So actually, I'll try and find it for next time. But there was an interesting video, I thought interesting video, of 5 of these guys floating around, but using them quite acrobatically, and more acrobatically than this, in that they would go up 30 feet, zip around, they would come down to sea level, they'd go in like dolphins and come back out, and etc. So we'll look for that next time. And so this might not seem relevant to what we're talking about with pipe flow, but of course you see the umbilical that's attached to this machine, the jet lev, is a pipe. And so what we could ask is, what kind of power plant do you have in this raft that's pulled behind you to be able to power that? And so that depends on, we've done some things with Bernoulli to talk about how high this thing can fly based on the velocities coming out of it. Do I need to do, have I gone back? I was just going to play it again while I was talking, just because we can. Yeah, okay. And so we could ask, what kind of power plant do we need to hold it in the air? We did some calculations already with Bernoulli and also Reynolds transport theorem for conservation of linear momentum to say what kind of velocity you need to hold it, I think 2 meters off the water. But then we assumed in that the normal requirements of Bernoulli are that the flow is inviscid, so there are no losses in the system. And so presumably pumping a lot of water quickly along a relatively thin pipe, relatively long and thin pipe, in other words a pipe with a long length to diameter ratio, may contribute to a large value of head loss. And so that's what we'd like to maybe finish up with at the end of our stuff today. So that's our plan. I just looked at a couple of other things in the news which I thought were interesting as well. This is out of Nature. I can't remember if it was last year or it was 2 years ago that Baumgartner was the guy who went up in a helium balloon up to 100,000 feet and then skydived out of there and finished out with landed with a parachute ultimately at the end, but ultimately was trying to do the highest dive. This is one that was done apparently not very long ago, 24th of October, so a week ago. And you see the spacesuit there, this guy. It doesn't look like a spacesuit, it looks more like a vehicle. But this guy, when he fell down, well, when he was free-falling, went faster than the speed of sound, so broke the speed-sound barriers. And we're talking about dimensionless numbers before the Mach number, so he was, by the look of it, at Mach 1 point something as he free fell through the atmosphere. And I thought this was an interesting example we did in class. It ended up on one of the exams, I think maybe last year, because when we talk about external flows, like internal flows, the drag on something on the internal part of the pipe is really a drag. We don't really think of it as a drag, we think of it as resistance to pumping, but it is a drag. And if you think of the pushing air around the outside of a pipe, it's not very different from air around a guy free-falling through space and being static and having the wind blow past him. There's a drag exerted on him. And so from that drag force, you can calculate what the equilibrium terminal velocity should be for that person. And maybe we'll do that. And so I thought that was an interesting event. And of course, the other two other fluid mechanics things in the in current lexicon now are this volcanic eruption in Iceland, which is the interestingly named Barabunga. Sounds like something Silvia Berlusconi should be doing, right? Bunga bunga parties. But, Barabunga is the Icelandic volcano which is not disrupting air traffic, but instead of spewing a whole bunch of ash into the air, which Iskjöfell did maybe 4 years ago and shut down European air traffic, this is putting a bunch of sulfur dioxide into the atmosphere with unknown implications for greenhouse gas behavior. And the other, I guess, volcanic issue, I mean, this is obviously an aerial volcanic issue, a kind of dispersion of fluids in the atmosphere. The other one, which is kind of a solid earth issue, is the Hawaiian volcano on Mauna Loa, which is slowly creeping towards this hamlet of 1,000 houses. And ultimately will probably just, well, it will erase it. It's tough to be able to stop. I can remember in the past, maybe 20 years ago, these kinds of advances in Iceland, you put a whole bunch of water jets on them to try and freeze the front and try and stop it, but nature's kind of an inexorable force that's kind of tough to resist. Okay, I guess I didn't open this one thing as well. So the other thing I want to open would be this courses. So you get to see someone's inner workings here. So it's this one, right? And so open with skim, so we can do something. All right. So so we'll talk about pipe flow. So we've said this before when we talked about non-dimensional parameters and similitude. There are these three requirements: geometric similitude, the lengths have to be matched in some way, so it's a true scale model. Kinematic similitude is that the Reynolds numbers have to be the same in the model and the prototype. And then if you do that, if you then notice that you have Euler number similitude, you can say something about the drag forces either on the inside of the pipe, so long as the flow regimes are the same, or on the outside of the pipe, or the outside of the aircraft. If you're looking at drag forces and lift forces, it's really the same problem. And so that's what we're attempting to do now. To be able to do that, as we get to where we should be, this is where we are. Okay, finally. When we talk about pipe flow, the expressions that we'll deal with, just to remind ourselves, are we use the energy equation in 1D, which is this Bernoulli equation, and we couple the terms with this. And so let's just write this out. We did this last time, but you probably never see this too much. Because it is just the fundamental expression that we'll use. And that is that if we write it from upstream, we have elevation, pressure, velocity squared term, the inertial term. We have a pump component in the middle. This is all upstream on the left. And we equate that to the same components downstream. This should be etched in your psyche. Someone should have a Halloween costume with this on the chest, on a t-shirt, instead of the Maxwell equation or something, which you see physics students wearing, used to. And two loss terms. Whoops. Head loss minor and head loss major. And just to remind ourselves, up, down, always has to be. Try like our sign convention. So this is the flow. And in terms of the pump head, what is it? HP is equal to, I've sometimes used P for power, but rate of doing work is watts divided by gravity times density times flow rate, Q. This term, of course, here is the mass flow rate through the system. Minor head losses, we said last time, and we'll explain today, are typically equal to a head loss, which is defined by the velocity head, v squared over 2g, multiplied by a loss constant, KL. And this is between 0 and infinity, I suppose. 0 if there's no loss, infinity if there's maximum loss, but usually it's not infinity, maybe it's 10, as we'll see today. It can be quite a large number. And finally, last but not least, is our head losses due to major losses, which are small incremental losses but large overall, are defined as a head loss being equal to friction factor, length over diameter ratio, and again v squared over 2g, the velocity term. The important things are that this is the downstream velocity, this is the upstream velocity, and this is the velocity in the system, which could be different. You could imagine if there were nozzles here, for instance, and that's worthwhile remembering. And that's about it, I think, in terms of that behavior. So remember those expressions. The other thing that goes with this is that with this major head loss is the Moody chart and the Colebrook-White formula, and it's worthwhile us kind of understanding at some level the significance of that. I won't bring up the Moody chart again. Well, I'll just flick back to it. It's this. But I'm going to draw the salient features that I think are important. So it gives us a friction factor, F. And it goes from a high number to a low number. So this is a big friction loss. This is a low frictional loss. It divides the chart into, importantly, 3 areas. And I'm going to just put those on the bottom. It scales it with Reynolds number, which is a velocity, a length, which is typically our characteristic length is the diameter of our pipe, and a density. So inertial forces over viscous forces, this is what it is. And it has markers maybe of 2,000 and 4,000, where it goes from laminar to fully turbulent. I can't remember, and transitional, I guess. And so for a circular pipe, the friction factor is equal to 64 over Re for a circular pipe, cross-sectional circular section. And that's, pardon me, that's only for laminar flow. When these laminae of water are sliding over each other, you don't have this turbulent eddies developed. There's this transitional region that goes into things and is, no, let me draw this properly, so don't draw that yet. Just want to draw this. So what I want to do is draw this line here, which is a smooth line, and this transitional region which goes from this curved portion of this curve to the flat portion. So those are the 2 parts I want to draw, I guess. And so let me do this. So this is this here is a smooth pipe where the roughness divided by the diameter is by definition 0. The large reservoir for Bernoulli means velocity equal to 0. Smooth pipe means a roughness of 0. And then this transitional line here, which gives this behavior that goes from curved to flat, absolutely flat, right? For all of these. So these individual curves are epsilon over d equals large, and epsilon over d equals small. So those are the kind of critical features that are interesting to note. And they're interesting to note because we realize that when we're looking at in the laminar regime, that if we wanted to, for instance, look at what this flow would look like, and so let me just, hopefully you have a bit of space down below here. If I know we're not looking at flow around a cylinder or a sphere, but in the laminar regime, if we looked at this flow, it would be this clinging flow that would go around the sphere and come out on the back side. And the significance of that is that most of the resistance is basically a shear stress that's applied on this side of this thing by the viscosity. And so it means that the force that's applied to this is applied really by viscosity. So you can imagine treacle flowing past this, and you can imagine if you had more viscous treacle, you might have to have a larger force hold it in place at a given speed of that treacle. If you look at the turbulent regime, in terms of things that we've looked at before, then the streak line behavior would be something that would come here, it would go around either side, and you'd get these vortices shed off on the back at different locations that then travel downstream. And so this is the turbulent behavior. And in this case it's indexed by some particular Reynolds number. It doesn't matter what that number is. But the importance now is that most of the drag is due to a pressure applied here by killing the velocity. And so it's actually the Euler number. EU is equal to delta P over rho V squared. And so this is kind of an essential difference between these two behaviors. In this laminar regime, all of the frictional losses on the outside of the sphere or the inside of the pipe is due to viscous behavior, and it's represented in the fact that this is a function of Reynolds number. In this turbulent regime, then all of the force you have to apply, the losses in the pipe in pumping, or the force you have to apply to be able to keep this thing in place with some kind of force, is due to the air from the jet engines hitting the truck and killing the velocity and pushing it over. And so for that reason, the frictional factor in that region is absolutely flat, which is great for some calculations, because if you know your Reynolds number is in this range, you have a single value of friction factor and you don't have to iterate to solve your problem. If your Reynolds number is in this range, you have to iterate to get a friction factor, and if you're driving flow by pressure, you might have to do multiple steps to solve your problem. So that's it. So it's important to get a feel for what this chart represents, and this is about the best picture I can give you of what that is and the significance of that. And in the transition, you're just going between these. So I guess the other thing is that if you have a very large roughness, then it kicks it into this fully turbulent regime at a lower Reynolds number. This number here is to the left of this place here. And I suppose the final thing is that if you have a smooth pipe, actually you never really get turbulent flow, because you don't have these little undulations to be able to kick it into an eddy, to disturb the flow, to kick it off into turbulence. And typically you need some kind of a perturbation, as it would be called in mathematics, to do it. You perturb the flow in some way, you bang it, and you kick it into... it's like putting water in the fridge. Sometimes you can get water in the freezer, or vodka in the freezer, which is below its freezing point, but is still liquid. You tap it, it nucleates, and suddenly it freezes. And so turbulence is a bit the same way. You provide a perturbation, an undulation on the surface, and you kick it into this other regime, which you can't get back out of again. And so that's it, right? So that's kind of where we're going with this. So we've made the point that this is what we want to be able to use to be able to define our behavior. The reason for spending a bit of time on this is that when we look at this friction factor, which we'll use for the Moody charts, this is all Moody. Sounds like an Anglo name. I don't know where he or she was from. Probably he in the days of this, but I don't know that for a fact. Then we see that the friction factor can typically be a function of Reynolds number. When we talk about these minor losses, which are due to the bends, so in other words, the summation of these, if you have, in this case, 1, 2, 3, 4, 5, 6 bends, then this summation would be on all of those bends. We said that this is just a factor which varies between 0 and something. And so if we're assuming that this is just a number, then often the implication is that when you're looking at flow in bends, because it's a bend, it's turbulent, and so you're in this regime where you can just give a single number for this friction factor, which you're applying here. So the assumption typically is for minor losses that the flow is turbulent because it's going through a fitting or around a bend, and therefore you just have a number applied to it. And so maybe we'll spend a little bit of time talking about this. So today we'll talk briefly about minor losses, how they conform to exit and entry losses. Then I want to do an example with the jet lev. So I don't want to spend a huge amount of time on this. So we've seen this, and we've made the point of what this head loss would be. And so if we know what this magnitude here is, we can calculate as a function of the velocity inside the flow system, not at point 1, not at point 2, but inside the flow system is the velocity we're looking for. We can calculate what this incremental head loss is. Often the assumption, if we wanted to, we could also define an equivalent length. So in other words, if we write this in the same way as we've written the major loss equation for flow in pipes, as some friction factor, a length of pipe and diameter, we could define, if we wanted to, an equivalent length of pipe over which this occurs. I'm not really sure why we'd want to do that, but we could do that, and that's why I'm not going to spend much time on it. We could imagine also that in addition to bends, there's also losses at entry into a pipe system and exit out of a pipe system, and we can characterize those in some way. The losses going out of a pipe system are quite easy to characterize. You're going at some velocity inside the pipe, and when you go into the big reservoir, you're going at 0 velocity, and typically KL in those cases, as we'll see, is equal to 1, because you're going from some velocity to 0 velocity. It doesn't matter about the shape of the exit or entry, but it just matters about the fact that it's going at some velocity before and none afterwards. It does matter for entry losses. So entry is into a pipe system, exit from a tank, and entry into a pipe system. And you can imagine that if you have a really disturbed flow that's going into this pipe that has to go through a convoluted system and has to therefore accelerate, change velocity, change speed and direction, then the loss would be larger if it's very convoluted versus if it's relatively smooth, or if it's really smooth with curved edges, or with really curved edges, that you can actually limit these. And so if you know what the entry into your pipe system is, you can figure out exactly what that loss is. And again, it's typically a number. This is our KL value, and so typically the assumption is that it's close enough to turbulence that we give it a number and don't worry about the Reynolds numbers effect. It's not lambda. So entry losses. Entry losses into pipe vary with the severity, if you like, of the disruption of going from some 0 flow here to accelerating it. If you look at quantifications of this, then this is just a figure that kind of shows that. If you have a pipe which has 0 radius, so 0 radius pipe would be this, then just as we saw earlier, the loss factor is 0.5. If you have a large radius pipe, as it's nice and curved, then the loss factor goes towards 0. So that's no different than giving a continuous variation between all of these cases here, right? And so if we need to get that, we can get that. But again, you see that because we're working with a single number, we're assuming that it's turbulent. If we look at exit losses, those are dead easy, because as we say, we're going at some velocity in the pipe, we're going at 0 velocity here, and no matter whether it's a big disruption, less of a disruption, or a tapered disruption, then all these numbers end up being of the same order. And so we can use those if we so wish. And so we can imagine that these minor losses that we have, entry into this pipe system, exit into the pipe system, and within the pipe system, I'm not going to worry about this, we can characterize in some way. And so it just becomes a recipe. The recipe we have for entry losses and exit losses are just the diagrams we've seen. The recipe for losses in individual bends depend on the conditions of the pipe. So if you're going around a 90-degree bend in a threaded pipe, so in other words, threads on the inside of the pipe make it rough and make it more turbulent and give it more drag, and so you'd expect that a threaded pipe has a bigger loss than one which has flanges, which is smooth. And you would imagine that a pipe which is going around a 90-degree turn versus a 45-degree turn, I think you'd probably think that the 90-degree turn would probably be larger than the 45-degree turn. So it all makes some sense, right? How much is it accelerating? Acceleration refers to not only change in velocity. Of course, there would be no change in velocity here, right? Same section here. Sorry, there would be no change in speed here. Change in section here is 0, but it's change in direction. So accelerating is a change in direction as well as speed. If you're going around 180 degrees, then you might expect those to be different. If you're going in a T, it makes a difference whether you're flowing along the T and this is just stagnant, which is what these numbers are for, versus whether you're going along the T and branching around it because you're changing direction and therefore accelerating, in which case line flow flanged, which would be this, versus branch flow flanged should be different numbers. And these are all determined experimentally, nothing more than that. And likewise, if you're flowing through fittings, like valves of some kind, it matters what the valve is. It matters whether it's a really disruptive globe valve, like these here, where it's going through here, down here, and out, and you screw this down to be able to close off this portion here, and you can figure out the magnitude of what this would be. So most disruption, this is the 10 that I mentioned. Well, I guess I didn't include this one, did I? So I guess the number should be infinity, but it should be larger than 10, so 200. And so as you start closing down these things, you could imagine that depending on how closed it is, it might make a difference. So again, I make the point that it's kind of formulaic. So that's it. So it becomes a recipe, and then we don't need to worry about it. Okay. So I don't know if there are any questions on that. I'm not very good at entertaining questions, but I'm happy to take questions. Let's go back to this for 2 seconds. And so presumably we could use that to calculate what we need to know about powering this raft that is towed on this umbilical to be able to lift someone up. And so we could figure out exactly what the magnitudes of the losses were. We could figure out what the power plant would be. I guess we could figure out what modifications we could make to it if we wanted to make it run more efficiently by, for instance, would we want to use a small umbilical connector, this yellow tube here, or we would want to use a large diameter one? What's the benefits of them? I think intuitively you'd probably think that you'd like to use a large one because the head losses in that might be reduced if you do that. So, no, it's the first time there's a lady on that one, I guess, right? So we've never noticed that before. So anyway, so let's look at that. Not that. And this. All right. So, how would we solve that problem? So, where are we? So let's really idealize this. What do we have? We have a pipe that comes up and goes down. Pipe is on a raft. And so how do we represent that if we want to? So I just, so it's a, so we're not going to worry about the weight of the person attached to it. We can write Bernoulli between a couple of locations. It could be this location, which we would choose as upstream. Could also choose this as upstream as well, right? I suppose, if you want to make life easier, because this is our flow line that goes through here and comes out here at point 2. And we had some things on here. So let's do the diameter of the pipe. Looked to me like it was 4 inches. 4 inches is a convenient magnitude. The area of the pipe, well, it is a round pipe, but square pipes are much easier. Okay. I think we said before that V2 was 10 meters a second. Can't remember whether we calculated that or not. 10 meters a second, I think, is 20 miles an hour, or is it the other way around? 5 miles an hour. I can't remember. I think it's 20 miles an hour, right? It's a factor of 2 different. And we'll see what else we need. I guess what else do we need? We need density. 1,000 kilograms per meter cubed. We use gravity on our planet. Well, sorry guys and gals. Close enough, right? And don't know if you've committed this to memory, but this is about right for water, is viscosity. And of course, pascals are newtons per meter squared, so it is all SI. And so what do we have? If we write our energy equation, we have elevation 1 plus pressure 1 plus velocity 1. Our pump plant, which is also a length, has to equal elevation 2, pressure 2, velocity 2, plus sum of minor, and sum of major. Okay. What are these? This is power. We used W dot before, but we've also used power, divided by the unit weight of water times Q, flow rate. We have head losses. Well, let's have a bend in here, right? So KL equals 1. So head loss is equal to KL times V squared over 2G. This is the velocity in the pipe, which actually will be V2, since we're not going to mess around with it. And we have our major losses, which are going to be equal to friction factor, length over diameter, multiplied by, again, the velocity in the pipe. Okay. So I guess we're going to need something else, and that's the length of this system, which is 30 feet. Is good, right? So we have some numbers. So we want to be able to solve for this. So let's talk about our variables. So what can we do? We could write it right here, in which case the velocity one would be finite, but let's write it on the surface where the pressure is 0 and the elevation 0 and velocity 1 is 0. That makes life easy for us. Choose a number for this. We could choose 10 meters. I guess we can't really because the pipe's that. So in the past I've chosen 2 meters. Sounds certainly a person's height. So this would be 2 meters. This would be the streamline velocity V2. It's entering into the atmosphere. So this would be 0. And these would be finite. And so if we rearrange this in terms of just this term here, everything else already actually is on the right-hand side. P over unit weight times flow rate is equal to V2 squared over 2G. Plus, missing something? Yeah. Plus the head losses, which are KL v squared over 2g, plus the minor losses, which are some friction factor which we don't know, length over diameter, v squared over 2g. So in this case, v is actually equal to v2, which is great, makes life easy. And so we could write this as our power is going to be equal to the unit weight of fluid, velocity 2 times the area of flow, multiplied by, I'm going to just take these terms out. Obviously, this term, all the terms are multiplied by v2 squared over 2g. And then this is equal to 1 for this. We said that KL is going to be equal to 1 as well. And we want to figure out exactly what this is. So what are these? So friction factor. Friction factor depends on Reynolds number. So if I zip down a little bit so we have some room.
Professor?
Yeah, shout.
I think you forgot the 2 meters from the height.
Oh yes, thank you. So this goes here. Great, thanks. So that's a bummer because now I had to put that in there and it's not multiplied by v squared over 2g. I guess I could divide it by, it could be z2 divided by v2 squared times 2g, right? Does that work? Still on the right hand side. Yeah, okay, so we'll come back to that. And so what's Reynolds number? Reynolds number is velocity, density, characteristic length divided by viscosity. Velocity was 10 meters a second. Density was 1,000 kilograms per cubic meter. Diameter was 4 inches. And viscosity was 10 to the minus 3 newtons per meter squared seconds, Pascal seconds. And so what is that? Hopefully a big number. So 10 and 10 to the minus 1 cancel, so it's 10 to the 6, right? Which is good. Because 10 to the minus 6 on our curve for friction factor, remember this is the smooth pipe, this is 64 over RE, Reynolds number versus friction factor. Then I think if we have a smooth pipe, which we're looking for, I'm not sure what I used in the past, then if this is 10 to the 6, then we can get our number from the Moody chart. So tell me if that number's wrong. I think it's right? But never know. Ten to the 6, smooth pipe is good enough. 10 to the minus 2. So friction factor is equal to 10 to the minus 2. And so we have that. So we know what this is. This is 10 to the minus 2. And length over diameter. Length was equal to 10 meters. Diameter was equal to 10 to the minus 1 meters. And so I guess that is 10 to the 2 times 10 to the minus 2. Well, that's 1, isn't it, actually? I think, right? So correct me if I'm wrong. So if we go back to this then and try and calculate what the power is, and what do we have? We have density times gravity, which is this. We have velocity 2 cubed times an area divided by 2 times gravity. I guess we don't quite get rid of that first term. Yeah, so does this end up being... So this first term is going to be a bit of a pain, but it's z2 divided by v2 squared times 2g. Does it simplify in any way? It's 2 meters. 2 times gravity is 20. Velocity was 10, so velocity squared is 100. And so that is equal to 40 over 100, so it's actually 0.4, I think. So this is 0.4, which is the z term. So this is the z2 term. What's this next one? This is the... This is the velocity coming out of the nozzle term, which is 1. It's always good to be reminded that we're running over. This other term is head losses minor, which is 1. And this term is that right? So 10 to the 2, 10 to the minus 1. Yeah, this is 1 as well, which is head loss major. And so these are the Bernoulli terms, if you like. These are the terms that come out from assuming that there's frictional inviscid losses. So this is inviscid, and these are fric losses. And just to do the final calculation, what do we get? So this should be 1,000. V2 was 10, so V2 cubed is 10 to the 3 as well. Area was 10 to the minus 2. Divided by 2, well, we don't care about 2. Multiplied by these terms. Let's keep them as they were. 1, 1. They're easy to add together. And so what does this say? This is... Oh, that's kind of a big... No, so it's not. So it's equal to 0.5 times, this is 10 to the 6, 5, 4. Watts. So it is, if you look at Bernoulli, inviscid, it's 1.4, it's about 5 kilowatts. Plant that you need to do this. If you account for frictional losses with this particular pipe geometry, then you basically add another 5 kilowatts to it. It's not 5, is it? I guess it's, no, 10 kilowatts, right? What am I doing? So this is 10 kilowatts. And I suppose this is about 7.5. It's actually 7, isn't it? 7 kilowatts. And so half of the, more than half of the losses in the system are due to viscous losses in the system. And so ignoring them would not allow us to do very good. Does anyone know the conversion, kilowatts to horsepower? Multiplied by what, sorry?
It's 746 watts per horsepower.
700 per horsepower?
746 watts per horsepower.
So it's about, so 1 kilowatt is about 1.3 horsepower. So this is about 10 horsepower, is that right? Sounds kind of low. And this is about, well, no, actually it sounds high. 10 horses? And this is 14-ish, is that right? I don't know if that conversion's right. but gives you can Google it. I won't Google it since we've run over. But the point is, you can do some very simple calculations to be able to give you order of magnitude, dimensioning of pumps to work on this. And it turns out that the viscous losses in the pipe are pretty substantial. Half of the energy you need to actually pull someone aloft. You can imagine if you, instead of being at 2 meters, you're at 4 meters, this term would double. You could imagine that if you used a pipe which was a smaller diameter, then the viscous losses would increase proportionally to the size, the reduction in the pipe. And so you can get some kind of reasonable feel for what those magnitudes would be. Okay? All right. I'm going to stop there. Thanks very much.